Assalamu alaikum. Welcome to lecture 9 of natural language processing. So today we will start a new section or new chapter in natural language processing. We will be discussing text classification. Text classification is a fundamental task in NLP, and it has several applications in NLP. We will start with discussing some applications of text classification, and then we will motivate text classification techniques, and then focus specifically on supervised learning approaches for text classification. And today we will start with the discussion on naive Bayes. And in the coming lectures, we'll also introduce logistic regression. And then subsequently, we'll be talking about classification and other models, machine learning models in terms of neural networks. So in the previous lecture, we had concluded n-gram language modeling. And at the end, we talked about the Knees-knee smoothing technique, which is practically the most popular in n-gram language modeling. So basically, the Knees-knee smoothing technique adopts several ideas. One of them is the idea of good Turing, which led to absolute discounting. The other idea was based on interpolation. And the third idea, of course, was the use of continuation probability to estimate unigram probabilities, or to estimate probabilities of lower n-grams. So, and of course, Knees-knee technique can be applied recursively to higher order n-grams by recursively applying the same technique to lower order n-grams. So, so before I get started with the new chapter, are there any questions? All right. So we have a quiz at the end of class today at 11:05. And we discussed, I communicated the tentative date and time for the midterm exam on email, I think yesterday. So we are still in the process of fixing a venue, and because of clashes and requirements by other classes, we might have slight changes in the dates and time. So please be aware of that. So for example, right now for NLP, looks like we have a slot from 1 to 3 on Saturday, not exactly in the morning, but that's still not confirmed. And as a consequence, we will probably have to move the data mining, which is the other course I'm teaching, to Friday night at 6:30. But again, that is still not confirmed. So I think there was some request that we should not have 2 exams on the same day. So maybe I think that request might be taken into account as well. So, but again, it's not confirmed. I will let you know maximum in a couple of days, but keep your calendar open for 4 and 5. So I was told that you cannot have on-campus exams on Sunday. So Sunday is kind of off limit. All right. So let's start with text classification. So text classification, as I mentioned earlier, is a popular task in NLP, and it has several applications. We will quickly discuss some applications briefly, just to give you an idea of the variety of applications to which text classification is a solution. So one of the earlier successful application of text classification was spam classification or spam detection. So essentially, spam is any message that is unwanted or undesirable, and we get a lot of spam on our emails. And nowadays, we also have spam on, for example, SMS messages on WhatsApp and even on Twitter and so on. So we would like to have an algorithm that would look at the text and tell us whether that is spam or not. And if it is spam, then it might be deleted or it might be moved to a junk folder or spam folder. So an algorithm that would do that would be a text classification algorithm to look at the message, the textual content of the message, and based on what is written there, it will be able to decide whether it is spam or not. So that is a popular application of text classification. Another application is author attribution. And in author attribution, the whole idea is that given the writing of several people, we would like to classify whether those writing belong to a specific person. For example, if you have person A, B, and C as potential authors for a given article, your algorithm should look at the article and say, okay, this is person B, not A and C. So again, that is an example of text classification. We are looking at the text, determining from the text who is the most likely author, and then outputting the appropriate label for that author. So on this slide, you see an example from history. Of course, this is American history. So there were several letters written that were unclassified. So a machine learning algorithm was used to find out who is the most appropriate author for those letters. So, so that's another application. Similarly, you can also use text classification to determine the gender of the writer. Again, a classification problem. We are given text that is written by some person. And by looking at the writing style or looking at other clues, we would like to decide whether or determine whether that is written by a male or a female author. So again, this is quite popular application nowadays in the context of social media, and especially in the context of advertising. So advertiser would like to know whether a particular writer is a male or a female, and based on that, they might want to target those persons for appropriate marketing programs. So author attribution as well as gender detection. So any problem in which you have text as input and as output you have some predefined labels, then that becomes a text classification problem. So another very popular application of text classification is sentiment classification or opinion classification. So, and you have seen such applications on the web as well. People write reviews of products and services. Some reviews are positive, other reviews are negative. We would like to have an automatic algorithm, a model that will look at the text and be able to determine whether that review is positive or negative. So in this example is about movie review. So if it is negative, then you might give it a label or a picture like thumbs down. If it is positive, then it might be thumbs up. And as you can see at some of these examples, some examples are, some classification problems are relatively easy. So, so unbelievably disappointing. So that would be thumbs down. So this is the greatest screwball comedy. So screwball is the giveaway word here. So this becomes a negative. So in other words, your model needs to be able to understand and interpret the writing, and based on that writing should be able to give an appropriate label to the text. So sentiment classification, another popular application of text classification. And finally, of course, there are tons of other applications as well. But among these slides, another popular application is topic classification. And you see this in, you need to probably do this whenever you have a library of documents. So we nowadays have libraries online, and we need to automatically categorize those documents. So maybe it is a newspaper website, and newspaper website has lots of articles. It will like automatically would like to group those articles according to some categories, like this is politics, this is sports, this is let's say science and technology, this is health, and so on. So that task can also be posed as a text classification task. Give it a article, and the algorithm, the model would tell you whether this is a health topic article or a politics topic article or so on. So in this particular slide, you see an application from the medical domain. So we have lots of publications in the medical domain, and also the medical domain has a well-organized taxonomy of topics. And ideally, we would like to group or assign a topic to each article, or maybe even multiple topics to each article. So that becomes challenging if we have lots of articles, and uh, for humans becomes time consuming. So we like something that's automatic and reliable. So again, an application of text classification. So any questions so far? So these are again the application that we talked about already on those preceding slides. So we can have spam classification, we have topic classification, we have author attribution, we have gender, or any other attribute of the person writing that article. So it could be, for example, from a particular writing, we would like to know whether that person is an introvert or extrovert, for example. So that could be a text classification problem. You can even have things like nowadays, there's a lot of hate and offensive language and toxic comments on social media. Given text, we would like to determine whether this is toxic or not toxic, or hate or not hate. So, and of course, based on textual writing, emotional classification is also a application that is popular. And this has applications in terms of psychosocial intervention as well. So all of us use messages, WhatsApp messages, Twitter messages, SMS messages. So you can have such an application running on your mobile, and the mobile would check your writing and determine whether you have some social or psychosocial issues. And if it is to a significant extent, it might even refer you to a particular medical help. So in fact, you can even call language identification a text classification problem. So language detection. So given a text in French, for example, and given a text in English, you would like to know whether this is French or not. So think of a computer who doesn't know languages, so you will need to determine whether a particular text belongs to a particular language. So let's move more formally into text classification. So what is the input to a text classification algorithm? Let's say we are kind of classifying, we are at the stage that we have a model and we would like to classify, use it to classify. So that model will take as input a document, and let's call that D. And then you have some fixed set of classes, C1, C2 to CK, let's say. And of course, these could be, let's say, spam or not spam, or these could be the topics, let's say health, politics, science, and so on. And your model would then select one of those topics as the most appropriate label for this document. So that is what text classification is. So of course, you might ask, maybe you can do this using building some rules. Maybe you look at some particular pieces of text in the document, and based on that, and based on the rules that you have developed, it might be able to classify this. But this is, of course, a, a, a difficult task, and of course, rules would change over time as well. So it's just not practically feasible. So hand-coded rules approach is no longer feasible. It wasn't even feasible in the 1980s. Before that, maybe it was somewhat popular. So nowadays, we basically rely upon machine learning, and specifically supervised machine learning. So in supervised machine learning, we need to learn the model. And to learn the model, you need to have a set of documents that have labels already assigned to them. The model, once the model is learned, then it can be used in the same way that we are shown in the couple of slides below. You give it a document, it gives you a label. So I'll come back to this later on. And there are lots of classification methods, supervised classification methods. So, and of course, there is some grouping and sub-classification within these classifiers. We'll briefly mention some of them later on. So some of the classifiers, popular classifiers for text are naive Bayes, logistic regression, SVM or support vector machine, neural networks, or you can call them deep learning if you like, and the k-nearest neighbor. So these are some of the most popular techniques that are used for text classification. All of them are supervised machine learning. And for those who have taken machine learning, you might have studied some of these techniques before as well. So in this course, we will focus briefly on naive Bayes, logistic regression, and neural network. We will not talk about SVM or KNN, although those are also relatively easy. So we'll focus on naive Bayes, logistic regression, and later on the neural network approach. Mm-hmm. All right, so let's, any questions? Mm-hmm. So let me build the setting for the supervised machine learning approach. So usually we have some training data, some data. So let's say D. So the training data D, it's a set, of course, of pairs. You have document and you have the label C, and let me say put I here, and I is equal to 1 to N. So we have a set of documents and their associated labels. So if I talk about a particular document, so D, let's say 1, it will also have a label C1. So D is a document, C is a label, and C, the labels comes from a fixed set of labels, capital C. Again, this is a set C1 to C2 to C, let's say K. Mm-hmm. All right. So C1, C2, C3 are labels. These could be, let's say, the topics of interest. And of course, we can always give them actual names, or we can just represent them with letters or just indices like this: C1, C2, C3, and C4. So there's K classes. So in general, when you have K classes, we say this is a K class classification problem. So K class problem. And the specific case of the two class problem is basically called binary classification. Okay. So if you have just two classes, let's say spam and ham, that would be binary classification. And in general, K can be greater than equal to 2. There could be more classes as well. So going back to our training data set D, as I said before, is the set of documents with the label. So you do need this to train the model. So once you have trained the model, we say that we have obtained a model. Let me call that, let's say G, the function G. So this is the model, which would take as input documents D in D, and it will output class C in C. All right. Of course, a slight notational, you can say, laxity might be shown here. Maybe I may not be 100% accurate in notation, but I think you understand the idea. So we have a function, or you can call it a model G. We have learned that model. When a document D is given to that model, it will output a label C from the possible set of labels capital C. Okay. Because previously I defined the data set D as two things, D and C. So that's why I'm saying there might be little issues in the notation. So generally what it is you have a population of documents, and from that population of documents, you have a sample of documents that are labeled, which is then our data set D. All right. Okay. So the task in supervised machine learning is to learn G. So we want to build or learn this model G. So, and we do this using the examples in our data set D. Okay. Once you have learned the model, then you can apply it to label new documents. So that is supervised machine learning. So now let's so let's me quickly go over some slides, and then I'll come back to the naive Bayes approach. Any questions? So the naive Bayes classifier is based on the Bayes rule, and it has an assumption which we talk about shortly. And more importantly, that I wanted to show here is that it relies on a specific representation of the document. So whenever you want to process something by computer, you will need to have appropriate representations. Here we are processing documents. So we need to think about how to represent documents so that a computer can process it appropriately. And the representation that naive Bayes relies upon or uses is the bag of word representation, which is a popular representation in text classification or text modeling or even IR, for example. So let's see. So let's say the function here that we have learned is gamma. Let's say I mentioned G there, so gamma. So to the function, you have given some text. So it's a movie review. So it has the whole text as input. And this model should then give us a label as output, which is either thumbs down or thumbs up. So here I've given the whole document as input, but appropriately, we would like to have a proper representation, which would be applied to all documents. So from this sentiment classification problem, you would like to find some features or important words that would help us determine the label. So if you look at this text again, you notice that there are some words that are more appropriate or you can say helpful in determining the label of this class. So words like love or romantic or whimsical may be sweet, for example, fun, for example, right? So these words would be helpful. And if you look at these words, most of these words are adjectives, actually. So one way to represent a document for sentiment classification is restrict yourself to adjectives. Just use adjectives from the document and discard the other words in the document. Okay? And let's say if we restrict ourselves to these words only, so we have only a subset of words that are possible in all the documents as feature words. And we will only focus on these feature words in each document while we are classifying. All other words would not be focused upon. So all the words would be discarded. Only those words that are of interest are kept. So you cannot think of the representation as a bag of feature words. Bag means that it's just a collection. So we have kind of lost the order in which those words appear in the document. So fun, sweet, love, all of those words would be jumbled up like in a bag. So, and if a word occurs and the number of times the words occur, that is only that is important. Its position no longer remains important to us. And based on that, we then make the final classification. Of course, you can further formalize this and build a representation which is in the form of a vector. So I'll come to this later on, and then you can proceed with the analysis. So the entire process is kind of shown in this figure. So you have document, you will have to process those documents, maybe do the text processing that we talked about earlier, tokenization, maybe you want to remove punctuation, maybe you want to remove all POS except adjectives. So things like that would be done. Based on that, you create a vocabulary. So vocabulary is a set of words that are of interest to you, the types that are of interest to you. In this case, it would be adjectives only. So if you have a vocabulary of size M, then you can build a vector of size M. And whenever a word occurs in a particular document, you write the count of that word. And in a vector, of course, there is no notion of order. So in a vector, the second position could be fun, the first position could be love, the fifth position could be sweet. We don't know in which position actually those words occur in the documents. Okay? So that's why this is called a bag of word representation. All right. Any question? So in general, we need to have a representation for D. Okay? So you can think of this representation as also a mapping. although it's not that essential, but let's say you can think of a mapping D, F from D to some, let's say, vector space X. Okay. So the document D, which is a document to represent a document X, maybe is a vector representation. I can bold it, and this becomes a vector. So any mapping from D to its representation would be a mapping function, representation function. Let's call that F. Okay. So for any X, we can use this notation ij, which is basically the ith document and the jth feature or word / type. Okay. Of course, types comes from the vocabulary. So vocabulary could be words, it could be characters, it could be subwords, as we had discussed already earlier. So word is an example of a type. Okay. So if you do this, then basically, and how many features do we have? So J would in general go from 1 to the vocabulary size, which if you want to call that M, so let's say V is equal to M. And as we mentioned earlier, there are N documents. So you can represent all the documents X in a matrix which is of size N by M. Okay. So this is a bunch of documents in our specific representation. Now, the question is, what is the exact value of Xij? So this in general could be any value. Generally, it will always be greater than equal to 0 for textual analysis. So we'll come to this general representation later on. First, let's go into naive Bayes and see which representation it talks about. But in general, Xij could be a value that is non-negative. It could be, for example, in the simplest case, it could simply be the count, which is actually the representation that one form of naive Bayes uses. But in other cases, it might be in points as well, decimals as well, not just integers. Okay, so is this clear, the notation and the setup? So let's now move on to naive Bayes. So naive Bayes, first of all, is a supervised machine learning technique, as I think all of you know. Within the machine learning domain, it's also called a generative model. And a generative models generally are probabilistic models. Generally, of course, not always, but mostly are probabilistic models. And the idea behind a generative model is you can use this model to simulate the data or to generate the data. So that's why they're called generative models. So naive Bayes is a direct application of the Bayes rule. Okay. So let's write the Bayes rule. So probability of a document D, probability of the class C, and of course I'm writing this in terms of variables now. Given a document D is equal to probability of document given class C, probability of class C, am I writing it properly? Yes, divided by probability of D. Okay. So ये Bayes rule है. Bayes rule of course comes from the product rule, and we have already seen the product rule before. Okay. So I've written D there, but instead of D, you can also write a representation, let's say X, the representation that we talked about earlier. So if I write the right hand side again, so probability of let me write X now, given C, then probability of C divided by probability of D, which is X. Okay. So this, let's say if you have computed this is our, we can say, the posterior probability of class given a document D or given its representation X. ठीक है ना, ये क्या था, लेफ्ट हैंड साइड पे क्या था, probability of C given X था. ठीक है, ठीक है, ये था. So on the left hand side, it will give you the left hand side, which is probability of class given X. So if you are able to compute the right hand side, you can make a decision right away from probability theory. Of course, if you go into deeper cost-based probability theory, वो हम machine learning में पढ़ते हैं, इधर नहीं हम पढ़ेंगे. But if it is uniform cost, then it's very easy. So if, let's say, there are two possibilities, probability of C is equal to, let's say, 1 given X, and then probability of C is equal to 2 given X. Okay? If you have obtained both of these probabilities, so which probability or which class would be the best for X? The one for which the probability is higher. So class is 1 if probability of C is equal to 1 given X is greater than probability of C is equal to 2 given X. And of course, 2 otherwise. Okay? So simple decision rule once you have the probabilities. And going back to our original formula, so if this is the case, and of course, if you have multiple classes, the class for which the probability is highest would give you the best label. So the best label, in essence, C star, would be what is known as argmax for all possible C's in C for our right-hand side, which was what? Or you can even say left-hand side, C given X. Okay? So what is argmax? Essentially, this is a way of saying that for whatever that comes after it, we will only return C for which that expression is highest. So we don't want the actual value, we just want the label. Okay? So we compute probability of C given X for C is equal to 1 and C is equal to 2, and return 1 if C is equal to 1 given X is the highest. Okay? So the right-hand side, of course, which I wrote C given X, can also be written in its components, probability D give, X given C, probability of C, probability to D. So if I do that, which would arg max C, so I can do that X given C, probability of C divided by probability of D, X. So here in the denominator, oops, copyright cancel again. So in the denominator, we have probability of X. So if we are evaluating one document X, one document D for which this is the X, so this expression, probability of X will remain unchanged, meaning that for C is equal to 1, you still have probability of X in the denominator. For probability of C is equal to 2, you still have X in the denominator. So if you just want to find the label, you can just find the maximum of the numerator and you can delete this part. ठीक है, तो ये delete हो जाएगा and still you will get the label, which is the best label. So you don't need to compute probability of X. ठीक है? So this is What I've written here is called the Base Classifier. Okay? So the Base Classifier is essentially on the right hand side, we have the probability of a document given a particular label, and then you multiply that with the prior probability of that particular label. Okay? And of course, we want to output the label for all possible labels. We will find the one that has the highest value. This, of course, will not be a proper normalized probability, but still the highest value would be the best answer for this. We would like to output the label that has the highest value. Okay? So now, so the naive-based classifier simplifies this. So there are two ways of looking at naive-based classifier. One way is simply thinking of X as a vector representation and then thinking of the naive-based assumptions. The other is just thinking of starting with X or D, which is a BOW, bag of words. So both way of looking at it is fine. So so let me start with the vector one. I think that would be easier for everyone. So we have probability of X. This X is, of course, a vector given C. Okay? So X is a vector, which means the probability of X. And I'm talking about a specific document. So I'm not going to write two indices. I'm going to write only the second index, J, which is the feature for this document. I जो है ith document का मैं नहीं लिख रहा. So I'm just going to write 1, the first feature, X, 2, the second feature, then X, M, the mth feature, given C. ठीक है ना? So this is now a joint probability of all of these features. Okay? And again, now making this is a joint probability. Again, estimating a joint from training data, as we had studied for language modeling as well before, would not give us good estimate. So you won't find this too many documents which have this specific combination of X1, X2, X3, XM. If you don't have too many documents with this specific combination, your MLE would always be 0. Okay? So what we do is we make the naive Bayes assumption, or the conditional independence assumption. Okay? ठीक है. I just noticed कि शायद आपको आवाज आ रही है ना, because थोड़ा सा मुझे पता चला कि शायद आवाज नहीं आ रही. ठीक है. So we break down this joint into products. We have that big pie. So if I use the LaTeX notation, product over J, so probability of X, J given C. So that whole expression would be reduced to this. Products of individual features given the class label. Okay? And then our full naive Bayes formulation then becomes C star is equal to arg max C from possible values of C, probability of C, then you have the product J, a probability of X, J given C. So this formulation is actually the naive Bayes classifier. Of course, this is all formulation. We have not estimated these values. So the next step, of course, is the estimation. Any questions? Okay. So what do we need to estimate? As you can see on the right-hand side, we need to estimate probability of C for all possible C's, which is the prior probability of the class label. And we also need to estimate probability of Xj for all J's for all possible values of C. Okay? And where do we estimate, from where do we estimate these values? From our training data. Okay? And estimates, we have already seen before, we have various techniques. MLE is one of them, and smoothing approaches are also available. But here, as we will see, MLE and maximum add one smoothing, or add one smoothing in particular, is the most appropriate. We don't need to go into more complex smoothing techniques like the one we studied for language modeling, which was, for example, we went up to knee smoothing. All right, any question? So we have about 15 minutes left. So I mentioned that there are two ways of looking at naive Bayes. One way is thinking of X as a representation and thinking of X as a joint probability, and then applying the conditional independence assumption and breaking those joint into individual probabilities and then writing the formula. So this is, of course, the more general way of looking at naive Bayes. The more popular naive Bayes that is used for text classification is called the multinomial naive Bayes. Okay? So MNB, multinomial naive Bayes. So as the name suggests, here we assume that the document D is obtained from a multinomial distribution. So multinomial, binomial, binary, categorical, I hope all of you have studied these somewhere. Of course, I think most of you must have also forgotten it. So, but in any case, let me try to explain. So what is for example, the Bernoulli distribution or the binary distribution? So the most typical example is the coin flip experiment. So a coin flip has two possible outcomes. One is the head and other is the tail. Okay? So if you flip a coin, what do you get? If you get heads, probability of heads, so this would be some probability. And since there are only two possible values, probability of tail would simply be 1 minus probability of heads. Okay? So this simple distribution is the Bernoulli distribution. So based on this, we have what is known as the binomial distribution. Again, taking the example of coin toss, but for n tosses, not just one toss. So meaning that you have a coin, you toss that n times, and then your distribution is over the number of heads that you see or tails that you see, anyone that you want to choose, the number of heads that you see. So let's say the new variable is m, let's say. M is the number of heads in n tosses. So this is the new variable. So then you have a distribution over probability of m. So m would be, of course, you have a probability for m is equal to 1. You have a probability of m is equal to 2. You have a probability of m is equal to n minus 1, and of course probability of m is equal to n. ठीक है? So this distribution is called the binomial distribution, meaning that you have a Bernoulli experiment which is done n times. So Bernoulli experiment here is what? A coin flip, which is done n times. In our context, our experiment would be a word or whatever type of interest we are interested in. So does a word occur or does not occur? And in a document of size n, how many times does that word occurs? Okay? But a document doesn't have just one word. It has multiple words. So that's why we have what is called the categorical distribution. Here the example would be a dice roll. So 6 possible outcomes. And just like that, extension of the categorical distribution to multiple rolls is known as the multinomial. Dice roll for n rolls. Okay? Meaning that now you have n variables. You have, in this case, dice has 6 possible values. You have 6 possible values. In this case, you have a variable of m1, m2, m3, m4, m5, m6, m6. ठीक है? And each of those mi would have value of either 1, 2, 3 up to n. ठीक है? Now इसको आप वर्ड्स के सेंस में ले लें. अब ये dice has 6 possible values. हमारा vocabulary size क्या है? Depending on the types that you have, vocabulary size, as we said, is V, and we gave the notation M there. So the M possible words, let's say we are considering words as types. So M possible words. So each of those words can occur in a document. Okay? So in other words, you have a dice of M possible sides. Okay? And then you have a document of length n. So you are rolling the dice n times. And then counting के उस m words में कितने words कितनी दफा आए. ठीक है? So do you get this? So this is the multinomial distribution. So if I change my variable slightly, if I call these W1, W2, W3 to W to WM. So M possible मेरी vocabulary size है ना, and each of these W is the you can say the count of that word in the document. ठीक है? So then this becomes a multinomial distribution. ठीक है? Or if you relate this W's to the X before, if previously X में मैं सिर्फ count से रखता है तो वो भी एक multinomial distribution ही थी. But X जहाँ मैंने पहले कहा था that is more general, उसमें कुछ और भी आप रख सकते थे values. ठीक है? So I hope now you appreciate the difference between the two. But as I said, most popularly for text classification, we use the multinomial naive Bayes, which is assuming that we count the number of times that each word appears in the document. And the idea behind this is that we consider that a document is a multinomial, is constructed through a multinomial distribution. Let's say a document has 100 words. You think of a dice that has M. M is a vocabulary size. Let's say vocabulary size 30, let's say. वो आपने dice with 30 possible outcomes 100 दफा roll की, and then you count के डाइस में वर्ड 1 कितनी दफा आया, 2 कितनी आया, 3 है कितनी दफा, 4 कितना आया, दैट इज W1, W2, W3, WN. ठीक है, it's possible that a particular word did not occur, which would be 0. It's possible that a particular word occurred many times, even it can occur 100 times, that's possible, but all the other would not occur. So that would be multinomial distribution. So iski probability according to multinomial is simply theory is product let's say J of probability of Wj raised to power of probability of Wj को कोई और term दे देंगे, you can say raised to power of Wj again. Wj count है. So if a word did not occur, so raised to power of 0 would give you a value of 1. Okay? And if a word occurs, of course, this probability would be multiplied as many times that that word occurred. So both of these would be identical to the previous one that I mentioned, as long as you took X as the count of words in a particular document. So any questions here? Okay, so next step is, of course, learning these probabilities. So let me start that. We still have a few minutes. Okay. So as we mentioned earlier, what probability do we have? Probability of C and probability of, let me write Wj now. Okay. Sorry, given C. Okay. So we would like to estimate these probabilities for all word, of course, in J, and for all classes C in our class capital C. So first, and of course, we have the training data set. So let's first look at C. So this is very easy. What is the prior probability of a class C? So this is simply, of course, by the way, ये class C कौन सी distribution होगी? If you think in terms of distribution, so you have k possible classes. So this is actually a categorical distribution. We are simply looking at k. You can think of this as a k-sided dice. वो एक दफा रोल किया है, वो देखा है कि उसमें 1 आया, 2 आया, 3 आया या k आया. ठीक है. So simply given our data set, we will first of all, फिर copyright लिखा गया है. Copyright को लिख रहा है. P 2 C आ रहे हैं. ठीक है. So probability of C is equal to, let's say, k, small k, is equal to so number of dogs in D belonging to class K, or meaning that CK, uska label CK hai, divided by total number of dogs in D, so which is of course n. Okay, so simply, of course, this is the MLE estimate, and for this particular case, MLE estimate is more than enough, because whenever you have a training data set, you will usually have multiple examples that belong to each class. So numerator में usually non-zero value होगी, or almost always non-zero value होगी. Denominator में, of course, total number of documents है. So let's say if you have a corpus D with, let's say, 100 belonging to C1, 200 belonging to C2, and let's say 100 belonging to C3. So 3 class problem hai. So probability of C is equal to 1 would simply be सो 100 डिवाइडेड बाय 300 400, ठीक है ना, ये हो गया. And simply this would also be equal to probability of C is equal to 3. ठीक है. And of course probability of C is equal to 2 would be 200 over 400. And all probability of course would sum to 1. So I think I will stop here. So we have a quiz in a few minutes. Any questions? So the quiz is 10 minutes long. So please keep a calculator handy. ठीक है. So एक आध कोई calculation होगी. And whenever you have a calculation in a question and you have given a box, तो थोड़ा सा आपने calculation की working भी दिखानी है. If you just write the answer, maybe we will deduct some marks. ठीक है. Maybe एक expression लिखना है before writing the final answer.
Sir, for this quiz, they have only allowed numerical answers. तो इसमें तो वो नहीं कर सकेंगे. Next time से फिर हम वो paragraphs allow करते हैं.
अच्छा, आपने अभी न्यूमेरिकल वाले किया हुआ है. अच्छा, ठीक है.
Yes, sir. इस दफा quiz में numerical.
अच्छा अच्छा, आपने, ठीक है. तो मतलब वो एग्जैक्ट खुद ही चेकिंग कर रहे हैं वो.
सर ट्राई करने से.
अच्छा, चलें, ठीक है, सही है. बट मेरे ख्याल से जो छोटे क्वेश्चन है उसमें बॉक्स ही रख दिया करें, बिकॉज आई रियली डोंट वांट के पीपल एक दूसरे से पूछ के आंसर लिखते हैं सिर्फ.
ठीक है सर, इसी दफा किया. नेक्स्ट
अभी तो
टाइम से
चेंज नहीं हो
दोबारा
सकते
बॉक्स में चले जाएंगे.
जी, ठीक है. अभी तो चेंज नहीं हो सकता. ठीक है.